So we're here at the example table, and in this video we're going to talk about integration by parts. So let's remind ourselves of the product rule. So this says that the derivative of f of x times g of x is the derivative of f times g plus f times the derivative of g. So now let's integrate both sides. On this side we recover f of x, g of x, and on this side we're left with the integral of f prime of x, g of x dx plus the integral of f of x times g prime of x dx. And it turns out that if we solve for one of these integrals, we get a very useful formula, almost the integration equivalent of the product rule. So let's solve for this one. So we'll move this integral to the other side. So we get the integral of f of x times g prime of x is f of x times g of x minus this other integral. So minus the integral of f prime of x, g of x dx. Turns out to be very useful. And in practice, we're going to use variables u and v very often, whenever possible. So we'll often write this as the integral of u dv equals u times v minus the integral of v du. And I actually don't memorize this formula, and I'll show you why in a moment. Let's look at an example. So suppose that we want to integrate x times cosine x dx. And remember that I said that integration by parts is almost the integration equivalent of the product rule. Well, you wouldn't use the product rule if you had something like x times x, because that's just x squared, and then you can use the power rule. But you would use it if you have something like x times cosine x, because these two terms don't interact in a nice way. And that's very often a clue, if you're dealing with integrals, that integration by parts is going to be something that's at least worth a try. So what do we have to do? Remember that we're looking for an integral of the form u dv. So we're looking for something like u dv, which means everything in this expression that we see has to become either the variable u or dv. So I'm just going to write u, and then below that we're going to figure out what du is. And then over here I'm going to write dv, and below that we're going to figure out what v is. So what are we going to set equal to u, and what are we going to set equal to dv? Here we don't have too much of a choice because we have two terms. We have x times cosine x. So it's almost true that in any case like that, one of the terms will be u, and then the other term, along with the dx, is going to be dv. So I'm going to set u equal to x and dv equal to cosine x dx. And in a case like this, if you don't know which variable to assign to which, just try. We'll talk a little bit more about why you might want to choose these two things. But the worst that happens is that you're wrong, and then you choose the other way. So u is x, du is dx. dv is cosine x dx. V is then sine x. Right? V is going to be the thing whose derivative is dv, and sine x has derivative cosine x. So how do we use this? Well, the formula says, well, I don't know what the formula says. I never remember. So here's what I do remember. I always set up this box. So I have u, du, and then dv and v. And I don't actually circle these, but you can think of circling them. So the first term is going to be u times v. And the second term is going to be the integral of dx and sine x. So, equals diagonal x times sine x, and then I subtract the integral of the product of the two bottom things. So, minus the integral of sine x dx. Now here's why integration by parts is useful. We took something involving an integral and turned it into some non-integral thing minus another integral. And this integral that we get here is simpler. That's why integration by parts is useful. X cosine x, not so simple. Sine x, fairly simple. So this is now x sine x minus antiderivative of sine is negative cosine and plus c. So why might we have chosen x to be u and cosine to be dv? Well, think about what we're doing with u. We're taking a derivative of it. With dv, we're taking an antiderivative of it. The thing that ends up in the integral here is the product of the two terms at the bottom. So this doesn't always work, but a good strategy to choose which term gets to be u, which term gets to be dv, is to choose u to be something that gets simpler. And x certainly gets simpler when you differentiate, because x just becomes dx. Cosine, on the other hand, doesn't become any simpler. And actually, that's usually about the best you can hope for dv. Choose something that at least doesn't become more complicated when you find the antiderivative. So cosine, it's a trig function. The antiderivative, it's another trig function. So we're not really making anything more complicated over here, and we are making something simpler over here. So that's a good basic strategy for determining which thing should be u and which thing should be dv. Let's look at another example. So let's suppose now that we want to find the integral not of x times cosine x, but of x squared times cosine x. So what do? Well, let's set up a little box. So we have u, du, and dv, and v. I'm not sure why I call this a box. There's no box there. Now we have to figure out which thing gets assigned to u and which to dv. Using the same idea as before, we want to find, if possible, one of these terms that gets simpler when you take the derivative. And just as before, this first term gets simpler when you take the derivative. If we set u equal to x squared, then du is 2x dx. Not quite as simple as before, but simpler than x squared. And then dv will once again be cosine x dx, and v will be sine of x. So what does this mean? This means, again, product on the diagonal, we have x squared times sine of x minus the integral of the product of the two things on the bottom. So minus the integral of 2x sine x dx. Now note this little style point. Dx always goes at the end. Always goes at the end. So even though we have 2x dx times sine x, always put the dx at the end. So minus the integral of 2x sine x dx. Well, now what? We're left with another integral. Before we just had something like the integral of sine. That's pretty straightforward. But now we have 2x sine x. So we need to apply integration by parts again. Now, in theory, there's nothing that says this integral can't require any other rule of integration. So in this case, this integral requires integration by parts again. So what do? Well, we need two different letters. We already used u and v, so just to make sure nothing gets confused, let's use r and t. So let's set r equal to something, and then we'll have dt equals the other thing. So this is similar enough to the previous example that we should know what to do. R is going to be 2x, dr then is 2 dx, dt is sine x dx, and t, well, the antiderivative of sine x is negative cosine x. So this thing becomes x squared sine x. That first term doesn't change. And now we're going to subtract this integral. So whatever we're going to subtract, let's put it in brackets, because this whole thing will tell us what to put in these brackets, and we're going to have multiple terms. So product of the diagonal, negative 2x cosine x minus the the integral of the product of these two things on the bottom. So minus the integral of 2 times negative cosine x dx. So what are we left with? We have x squared sine x, still unchanged. X squared sine x minus a minus, so we get plus 2x cosine x. Now, how many minuses do we have? We have a minus, and a minus. So this becomes minus 2 times the antiderivative of cosine, which is sine x. And finally, plus c. So those are some integration by parts examples.